So let's begin with part one. How do we evaluate different linking theory proposals using developmental modeling? And so our goal is to build a modeled learner who learns close enough to how real children learn to actually tell us something informative about these linking theory proposals. So a really great question is, what does close enough actually mean? And so I say that it means close enough to this process over here, which I talk about more in a recent book chapter, but it's really capturing what I think are really key components of the language acquisition process, both external components that we observe, like the input the child gets and the behavior that they produce, and internal components, which is all this stuff that we try to infer on the basis of the input and the behavior, right? And this has a lot going on in it, right? And so when we're developmental modeling, I think it's helpful to think about 5 main parts of this rather complex process. So the first is the initial state. What does the child we're modeling, what do they start with? What knowledge or abilities and learning biases does this child already have that allows them to extract signal from that input, that allows them to decide what to learn from, that allows them to do inference, that allows them to turn their developing grammar in, via their engines of production into observable behavior? Like, what are they starting with, right? And in the case of our linking theory stuff, what linking theory assumptions are they starting with? Then we talk about the data intake. So how does the modeled child perceive the input that they're getting, right? How do they extract signal? What signal are they able to extract, which becomes their perceptual intake? And what part of that perceived data, that extracted signal, is actually used for acquisition, which is the acquisitional intake over here. And so the kitten was blicked by a little girl is an example of an input that they might get. And on the basis, say, of the linking theory's assumptions that they hold, they might interpret, they might learn from this, extract from this, that this is an instance of 2 movements. Things are not where they expected them to be twice, or maybe they're encoding more of the details with respect to a fixed representation or with respect to a relative representation, right? So your initial state assumptions are going to affect typically what you're actually learning from in your modeled child, your acquisitional intake. So then how are updates made to the modeled child's internal representation? That's where learning is actually happening, this inference to actually update that developing grammar, your ideas about how your language actually works. And then the learning period is this iterative incremental process that this keeps happening for some amount of time. We typically think about this in terms of years or months. In modeling, we might think about this in terms of how much data you get access to, but it's the idea that you keep doing this updating process some amount of time, and that's how long the child has to learn. That's a learning period. And then the target state. So what does successful acquisition actually look like? What knowledge is the child trying to attain? That's the developing grammar here, often assessed in terms of the observable behavior, which, as you can see, actually goes through whatever the production engine is to get the behavior we observe, right? But you try to often infer what the developing grammar looks like on the basis of that behavior. That's your target state. So in the case of our linking theories, for the little girl blicked the kitten on the stairs, one behavior is actually interpreting this the way adults do. Another one is clustering verbs together, our verb class knowledge. So even if we don't know what blick means, the fact that blick might be kiss or pet or touch or hug, that these get clumped together in that child's developing grammar. They're inferred classes on the basis of their input. And we can try to, again, backtrack what that looks like on the basis of the behavior that they're producing. So do they interpret these verbs the same, or do they produce them in similar contexts? And from that, we might infer that they are clustered together into the same verb class. So if we can define these pieces, right, again, which captures a lot of stuff going on here, we can make sure we've captured the relevant parts of this acquisition process in our modeled learner, which is the goal. So let's do this for the modeled learners who implement different linking theory proposals, right? All these guys up there. So, okay, what's our goal? Let's be very specific. We're going to model the developmental trajectory of verb class knowledge from 3 to 4 to 5 years old in English, because this actually corresponds to the empirical data we have access to. And so in the initial state, we're going to have different types of linking theory assumptions about thematic systems, about whether or not there's already an expectation of a mapping between that thematic representation and the syntactic positions of subject, object, and oblique object. And so one thing to ask yourself, is this plausible? Is this like going to be a model that could be a real child? And there's reason to think that thematic roles are not crazy. Thematic roles indicate event participant roles. They're very salient to very young children. In fact, there's evidence that even under a year, children are sensitive to what participants are doing in an event that correspond to thematic roles. So that's good. And it turns out that in addition to that, children are also sensitive to the animacy of the verb argument. So the fact that the girl and the kitten are animate but the stairs is inanimate is something that very young children are sensitive to and actually use when figuring out which verbs go together. So this idea that you'd be using that for verb class knowledge is not crazy. And it turns out children also pay attention to the linguistic context of a verb, what we're going to call its syntactic frame, to figure out how it behaves, to figure out which verbs should be clustered together. So in the case of the little girl blicked the kitten on the stairs, the idea is that you would have a noun phrase before the verb, a noun phrase after the verb, and a prepositional phrase on the stairs after that. So this would be the syntactic frame that you're able to extract, that you have the ability to notice and to use. And so that's all the stuff that's going on in our kids' initial state in terms of the knowledge that they're getting. And then we think about where they're getting that knowledge from. What we use is samples of child-directed speech from the Child's Tree Bank that my colleague John Sprouse and I compiled a couple years back. And we have a lot of realistic samples from children under the age of 3, under the age of 4, and under the age of 5. You can see sort of the details of how many utterances and how many verbs, and the answer is, quite a few. Right, and so this is the input that's going to yield our data intake. So when we get something like the little girl blinked the kitten on the stairs, we're going to be able to extract all of that information that we saw before. In addition, with respect to the syntactic frame, there's also this choice of whether children should pay attention to the surface morphology on the verb. So the fact that blick has that ed past tense ending is something that children could note, right? And then sort of include on the syntactic frame. And so blicked would be different from blicking, which would be different from blicks, right? Present and past and progressive, right? Or you could lump them all together and just ignore surface morphology. So if you heed surface morphology, you're creating more frames, right? You're sort of having maybe sparser examples of any individual frame. If you lump them all together, you're having more examples of any particular frame because you've abstracted away from the surface morphology, but maybe you're losing some valuable information there about how verbs are behaving that could help you make these verb classes. So this is an option that's going to be encoded really on the data intake. Are they paying attention to surface morphology and encoding the fact that it's blicked or not, and really just encoding the verb argument structure. So they're going to have that. They're also going to be encoding our animacy of our different verb arguments, and of course they're also going to be encoding the specifics that are related to the linking theory assumptions. So if they expect a mapping already, this would be a case where everything is exactly where they expect it to be, so 3 instances of no movement. But if they don't expect a mapping, they're going to be encoding the details of what's going where. In a fixed representation, the fact that the proto-agent's in subject and the proto-patient's in object and so on. In the relative representation, the fact that the highest is in subject, the second highest is in object, and so on, right? So more details of the distribution of these different thematic representations. So that's all our data intake. And then what will we do with that? And the basic question we're setting out to answer is it possible for the child to use that acquisitional intake to achieve the target knowledge or behavior? Right? That's our very basic question. And so because of this, we're going to be using an ideal learner model. It's my ideal learner baby here, right? But why? Well, an ideal learner model is not concerned with the cognitive limitations and incremental learning restrictions that children have, which is often what a learning period is encoding, that you're learning incrementally. Here we're going to abstract away from that. We're just going to say, if you get the batch of data that these kids get, are the assumptions that you have because of those linking theories actually useful? Do they get you, right, to the kind of thing that children actually do, right? Are these the right assumptions? So we're going to abstract away from learning period, and instead we're going to be using, we're going to focus on how that inference process is working. So learners are going to be using a generative model of how the observable data for each verb are created, and that's encoded here in this delightful plate diagram, right? So this is meant to encode all the different types of information that children are using from that data intake to infer the verb classes. So just to walk you through it, the idea is that for each verb, and we have however many verbs we have, so a verb like fall, each verb appears in a certain number of instances in that input. So these are examples of fall that actually come from the Child's Tree Bank. So it's falling off, she fell down, don't fall, is London Bridge falling down, right? Instances, right? These are utterance types, right? And then each instance may be observed some number of times. So the utterance tokens, I'm not sure why we have a square there, but it's falling off. That's fantastic, right? So you have this distribution of instances for each verb, and that's what you're really observing. So then what you're trying to do is to figure out what class each verb belongs to on the basis of that distribution of its behavior, right? So maybe fall belongs to class 7 or something, right? But you're trying to infer the verb class that generates that observed distribution of instances. And the learner doesn't know beforehand how many classes there are or which verbs belong to which, but there is a bias for classes in a power law distribution where a few classes have a lot of verbs in them and most classes have very few verbs in them, right? And that's a property that natural language tends to have, in fact, nature tends to have in general. And so that is a bias that is built in, but nothing beyond that, just the fact that this is the kind of class distribution you should expect to see. And then depending on the verb class, right, the observed usage that we see down here will have certain characteristics which are encoded here. So these may be binary characteristics, such as whether the subject is animate or not. Maybe in the case of it's falling off, it's inanimate, and each class has a probability for preferring each option. Maybe this class tends to prefer inanimate subjects, right? So this is the kind of thing you're tracking. And the binary choices that our learners are going to be tracking are the animacy of the subject, the object, and the oblique object, and when you expect a mapping already, if there's movement or not, how much, movement or not movement, right? That's your binary choice. Then, these characteristics also include multinomial options, such as which syntactic frame, what's the distribution across syntactic frames that a verb appears in, right? And so you're going to have some probability of preferring each option, and then the multinomial choices include that syntactic frame distribution, and if you don't already expect a mapping, then the distribution of these thematic representations across the syntactic positions. So that's going to be a multinomial distribution you're going to be tracking. So then, that's the information. That's all the information up here. So using the observed instances of your verb usage, we're then going to use Bayesian inference, right, to determine a couple of things. First, how many classes there are. Second, which class each verb belongs to. And third, what the characteristics are of each class. All of that is going to be inferred by our learner by doing Bayesian inference, right? And so the best answer is going to maximize the probability of the observed data. That's your best hypothesis for how your language works. And so this is some of the math that's associated with this. It involves Gibbs sampling. And so that is an idealized inference process. So Bayesian inference can be done in many different ways. This happens to be one that corresponds to an ideal learner because it's guaranteed to converge on an optimal answer if you give it enough iterations to run, right? So we're just trying to see if this information, if the assumptions that we've built in, right, on the basis of these different linking theories, get you the right verb classes for kids, right? And so this part right here is really what makes this an idealized learner, as opposed to, say, a less idealized learner who would maybe approximate this inference process. But the idea that you would be combining information together in this way, that is not crazy at all. That is not idealized at all, right? It's just the inference, the way you're carrying out inference here, that makes this an idealized inference, an idealized learner. So the basic question then, is it possible for the child to use that acquisitional intake to achieve the target knowledge and behavior? So our goal really is to determine if the information provided in the modeled learner's acquisitional intake, that thematic linking information, the conceptual information of animacy, the syntactic frame information, is that sufficient to identify verb classes the way children do, right? That is our question. So, okay. What does that look like? How do children do that? What does the target knowledge or behavior look like for verb classes? And so our goal, just to remind ourselves, is to model the developmental trajectory of verb class knowledge from 3 to 4 to 5 years old in English. So what does that look like, right? So I did a survey of 38 experimental studies on children's production and comprehension of specific verbs, and from this emerged 12 different behaviors, ways that verbs are used or interpreted. And these are used to create a number of verb classes, where each verb class is a combination of one or more of those verb behaviors. So for example, at 3 we might have, these are some example classes, you might have a class of verbs that are known to be passivizable, but we don't know anything else about them, as opposed to ones that are known to be passivizable and also take that complement clauses like C, as opposed to ones that are not passivizable, right? So we get these different clusters of verbs on the basis of their behavior. And at 4, some shifting around, so now we have more that are passivizable. We also have more syntactic frame features, so want is used in a variety of different syntactic frames. And then at 5, again, we have more shifting around about what is or is not passivizable, and again, more combinations now with things that are known to be passivizable, and also take some of these additional syntactic behaviors. So again, these are the verb classes that we're trying to learn, we're trying to match. And so it actually works out to between 15 and 25 classes of between 60 and 84 verbs total in these classes. And this is what we would like our modeled learners to match, to be able to say, ah, yes, they have learned the verb classes that real kids seem to have in English at these ages. So that's the goal. How does evaluation work? How well did our modeled learner do at finding, at inferring these verb classes? And so to do that, the implementation we use is the RAND index, RI for short. It ranges between 0, which is very sad, to 1, which is perfect. And so the idea is that you get credit for putting things together that belong together and keeping things apart that should be apart. So in particular, for each pair of verbs in the inferred classes that come from these modeled learners, right, the child's classes, these two verbs could truly be in the same class, so they should be put together. And if in the inferred class you put them together, that's good, that's a true positive. Or, exciting true negative there. In the child classes, they could truly be apart. They could be in different classes. And if in the inferred classes they were also apart, then this is a true negative. So you correctly kept them apart. And then if you messed up, then you have false negatives and false positives, right? So the RI is simply the true positives and true negatives over all of the different classifications that you made, right? So it's very intuitively nice that way. It seems to give you credit for exactly what you want. But how do we know that we're doing better than chance, right? You can get some score, maybe 1's better, 0's not great, but how do we know we're doing better than chance? And so what we decided to do was to bootstrap confidence intervals for the RI with randomly generated classes of random size and random verb assignment, where if you're doing better than 99% of those classes, we're going to say that you're doing better than chance. And if you're doing worse than 1% of them, you're doing worse than chance. Luckily, none of ours actually fell in that range, but we're really focusing on which ones were actually better than chance. So, as a reminder, we're comparing a couple different thematic systems, a relative system where we have this hierarchy and a fixed system where we have 3 fixed categories. We're comparing whether the learners already expect a mapping and so are just encoding things in terms of movement, or don't already expect a mapping and are so encoding the details of where these thematic representations are appearing. And we're also encoding in the data intake part, are you paying attention to the surface morphology on the verb, or aren't you, right? So each modeled learner is going to implement one of these, a thematic system, an expected mapping assumption, and something about surface morphology. And these are the ones we're going to run and see which ones are best at matching the observed classes in 3 and 4 and 5 years old. So here's what we find at 3. There are a couple of learners that are better than chance, that do good, right? And both of them use a relative thematic representation. They both ignore surface morphology. But, the one that has the link already does fine, one that doesn't have the link already does fine. But at 4, it shifts. Now it's the fixed one that's in that same position of the thematic representation. Still no morphology, have the link, don't have the link, but you're the fixed representation now. Or another option is you could not have the link, pay attention to morphology, and then it doesn't matter whether you have fixed or relative. So a couple more options going on for a match at 4 years old. And at 5-year-old, we get even more, right? So the main thing is that you can have the link and then it doesn't matter, a fixed or relative representation will work, ignoring or heeding morphology will work, fantastic. Or you could not have the link, but then you have to ignore morphology. And you could have either the fixed or the relative representation. So this is a lot of stuff going on, right? So we've got a bunch of different learners that will work. So it's nice that, learning from this kind of information will work in some respect. That's fantastic. That's new. But maybe more interestingly, how do we interpret this with respect to our linking theory proposals from before? So let's look at Utah, which says that you have a fixed representation and these links to the syntax are innately specified. So early maturation would assume that these two pieces of knowledge are present at all ages together. And that is a problem, right? Because the thematic representation isn't there at 3. Only the relative one is compatible, right? It's not there at 3, even though the link could be. So the good news, of course, is that these two assumptions, the thematic representation and the link, are there at 4 and they're there at 5. So what we see really here is that Utah is compatible only with late maturation of the respective knowledge at 4 or later, right? Well, what about Ruta? So again, the idea is that you have this time a relative representation, and the link is innately specified, so early maturation is going to assume that these two things are together at all ages. Are they? Well, sort of, right? So at 3, great, they're there together. 5, great, they're there together. 4, oh no, they're not, right? So you can either have the link, but then you have to have the fixed representation, or you can have the relative representation, but then you can't have the link, right? So what's going on here, I think, is that development's more complicated for an early maturation story. The knowledge has to somehow be inaccessible together at 4 for some reason, right? So maybe what we're looking at really is late maturation, and that, you know, you don't actually have it here. You don't have the link yet. You have the relative representation with no link at 3. You have the relative representation with no link at 3, but then at 4, excuse me. But then at 5, now you have your relative representation with the link. So we have late maturation would be compatible and would kind of be an easier story to sell for Ruta. All right, so those are our innate theories. What about our derived theories? So we have our fixed representation, and so the derived mapping variant of this one would look for this knowledge to be present after the child has had sufficient language experience. So no link and then link, right? But you always kind of want to have that fixed representation. And same problem, right? You don't have it at 3, so you're going to have to derive not only the link, but also the fixed representation, right? And, you know, maybe you can do that, but that's like an extra piece, is derive that fixed representation at 4, and then you could derive the link at the same time or thereafter, right? But you don't have it at 3. So you need to derive that fixed system. Now for the relative system, phew, things are looking a little better here. So relative, again, we're looking for the relative representation. We're looking for no link and then a link. And here at least we see an easier path, right? This seems compatible. So for example, the relative representation is there always, and maybe you don't have the link at 3, you don't have it at 4, but you've derived it by 5, right? That's one path through, totally easy, derived mapping, relative representation there the entire time. Phew, life is good, right? So what do we take from this? So here's what I think we take from this. So I think one of the really cool things is that our linking theory proposals can now be coupled with the developmental theories that have to accompany them in order to match empirical data for children, right? So in particular, innate mapping approaches like Utah and Ruta have to involve late maturation, or at least that's the simplest way to explain what's going on, right? You need to have that happening late, not early the way it's typically talked about. And second, approaches with a fixed thematic system, so classic Utah and its derived mapping variant, they have to involve either late maturation of that fixed representation or derivation of it from the input. I mean, it's possible, right? But you just can't have that, right? That needs to somehow be learned or developed as well. And maybe that's not something that we really thought about before. And so this, I think, leaves us with some pretty basic questions now. So if knowledge matures late, whether it's the linking knowledge or the fixed representation, how does that work? I think we need evidence from developmental neurobiology to tell us why we see this delay, right? If, on the other hand, knowledge is derived from the input, great, but how does that work? We actually need a concrete proposal for how children could do this. And that's really where I want to turn for the second part of this talk, was just to say, how could a linking theory be derived from children's input?